This is Lab 2, Magnetic Field of a Bar Magnet by Frank Ragone. So for this lab, the purpose was to understand the impact of distance and location of a magnetic field due to a bar magnet, and then to visualize this through GlowScript. Some of the findings in the lab were that the magnetic moment was 5.22 amps times meters squared. The measured magnetic field overall was 7.34 times 10 to the negative fifth Teslas, and at the 45-degree angle, the magnetic field was 1.29 times 10 to the negative fifth Teslas and 3.87 times 10 to the negative fifth Teslas in the y direction, and this distance was 0.272 meters. As for the fundamental physics principles used in this lab, we used the Bivet-Savart law, which is this equation right here. It was used to calculate the magnetic field as a vector at a 45-degree angle with the bar magnet, and then the magnetic field due to the bar magnet was used to calculate the magnetic moment based off of the slope and the intercept of the graph of the natural log of the magnetic field and the natural log of the distance. The setups and the assumptions for this lab was that to set up the Magnometer app with the Earth's and then align it with the Earth's magnetic field so that it's not interfering with the data collection, then measure 3 trials with the different magnetic values at different distances, and then it was to set up a 45-degree angle and figure out what the distance was when it's 100 UTs. And then as for the assumptions in the lab, the bar magnet is going to act as the only force in the system and it acts as a dipole, a magnetic dipole. And then as for the system would be the bar magnet and the surroundings would be basically nothing because the Earth would be canceled out. So after data collection, these were the results of the lab. Our n value, which was taken from the slope, was negative 2.481, and then our intercept for ln of k was negative 13.771. The other key details was that the distance was 0.272 approximately, and then this led to the calculations of the magnetic field, or the magnetic moment, being 5.22 amps times meters squared. So to visualize this, I use GlowScript, and the first equation used in the top left was the magnetic dipole equation, and this is using Bivet-Savart's law as discussed in the prior slides. And then when we look further down in the code, you can see that I've set up the 6 different observation points that were going to be used around the dipole, and then I calculated the 2 ones that were on axis using our prior dipole equation, and then the final equation on the right was at the 45-degree angle, how to calculate what the magnetic field would be. So this was the resulting GlowScript model after running the code. Some key things to note is that the distance was the one used from the data collection, being 0.272 meters, and then the magnetic field at that 45-degree angle ended up being that number at the bottom, measured in Teslas. And when you get the magnitude of that, that should be similar to the priorly collected data value of the magnetic field. Some of the possible errors could have been that the rounding of the values for distance and magnetic field, which could have led the GlowScript model to miscalculate the values. Some of the other ones could have been that there was a slight calibration issue with Earth's magnetic field, which means that the Earth would play a part in the experiment. And then the last issue that could have been was that the Magnometer app could have had misreadings due to sensor parts not being calibrated in the phone. Some of the concluding summary questions was that when the magnetic meter is far away from the magnet, it's measured at a near zero magnetic field in the x direction. This is true because when distance goes up, the magnetic field is going to go down. And then as for the last 3 statements, they basically summarize the same thing, except one states that it's decreasing, the other says it's staying the same, and one says it's increasing. But the true one is as the magnometer approaches, or as the magnometer moves closer to the magnet, the x component of the magnetic field increases, because as distance goes down, the magnetic field goes up. So for the final conclusion questions, the first one basically states that if we didn't calculate for Earth's magnetic field, how would the results have changed? the overall magnetic field would have been slightly different because the Earth would be acting on the system, and then this would also split the resulting magnetic field into component vectors for certain positions. And then the other what if question being that if you had two identical magnets stuck together, this would end up increasing the strength of the magnetic field in the same direction because the magnetic moment would be doubled.